Hello, in this video we are talking about some must-know IB physics stuff. As you're getting ready for those IB exams, this is the most foundational kind of basic stuff that you want to feel 100% confident about before you get into some real review and practice. So you've just got to know it, no excuses. So here we go. Okay, number one, the absolute bare minimum preparation you need to do going into the exams is you need to know every single thing in your data booklet. You have to know what every letter represents. What are the standard units we use with them? What's a vector versus what's a scalar? Remember, they don't show you in the data booklet because you're supposed to know it. And what are the special rules for each equation? Because there's plenty of equations that have like limitations or rules, or you can only use them in certain situations. All right, you need to know all that stuff. This is like, again, the kind of bare minimum prep you need to do. You get the data booklet on the exams. It's your best friend. So treat it well, study it well, and make sure you know everything in there. It's a good idea to practice with the blank data booklet because that's what you're going to have, and you want this thing to be, like an extension of your body. Just as soon as you know what equation you need, without thinking, you'll just like flip right to the page, know right where it is on the page. You know what I mean? I do have a little annotated data booklet that you can check out, which can help you study if you want to double check and make sure you got all the little details down. Make sure you're practicing with the blank one. So, for example, we got a couple different ends here. They mean totally different things. You want to make sure you know what's what, so you're not stressing about it on the test and you know exactly where to go. Okay, the most crucial, probably definitions in all of physics are work and power. Work, power, and energy are fundamental, some of the most fundamental rules in science, period. And they come up everywhere. They'll come up in every single unit. Whether you're dealing with a box on a ramp or doing, nuclear physics, you're going to be talking about energy and rates of transfer of energy and such. So make sure you know what work is. Work is delta E. That equation's not in the data booklet because that's our basic definition of work that you need to know. Work is like final minus initial energy. So always think about if something is gaining energy, losing energy, if energy is being transferred from one thing to the other, work is being done. The amount is the work. You do have this equation, which is a nice equation to find the work done by a force, but this is like the fundamental thing you always want to be thinking about when you think about work. 1 watt is a joule per second. Maybe the most important piece of information that you should be able to like regurgitate without thinking. All right, that unit, breaking down that unit is so crucial to doing so much physics. Yeah, so power is the rate of energy like flow, how quickly work is done. For some stupid reason, they say delta W over delta T in the data booklet, which is wacky. Nobody does it that way. This is a better way to say it. Delta E over delta T, change in energy over change in time. It's the rate of flow of energy. Yeah, make sure you know those two things. Another really good something per something unit is the volts, which is a joule per coulomb, which comes up also all over the place. So our definition of potential difference, for example, electric potential difference, it is work per unit charge, to blah, blah, blah. You have two versions of equations that tell you this in the data booklet. Here's the one that everybody has in B.5. With the circuit stuff, like voltage is work per unit charge. D.2 is officially an HL section, but I like this version better. This is the same equation. But here they write delta VE to emphasize that it's the electric potential difference. And you could multiply charge by an electric potential difference to get work, because that's what a volt is. And we've done this so many times, right? You like often have something like there's an electron being accelerated between two plates over some voltage. Well, if I multiply the voltage by the charge of the electron, I'll get the work done on the electron. That probably maybe here equals the kinetic energy that the electron gains, so I could figure out how fast it's going. That stuff we do all the time. You got to know that you can do that, and that's because a volt is a joule per coulomb. Other examples of this are definition of EMF. EMF is a voltage thing, and that's work per unit charge for the battery to like power the whole circuit. You can think about if you got like a voltage across a resistor, you want to be thinking about joules per coulomb, like, 5 volts. That means every coulomb of charge that goes through the resistor generates 5 joules of heat energy. So thinking about a volt as a joule per coulomb is super helpful for all of this electric field stuff. Some thermal physics things that are good to know. A lot of this comes down to the thinking about the particles to explain the big scale macroscopic behavior. And the most important is like your 2 types of energy and what they go with. So temperature is all about the random kinetic energy of the little particles as they're bouncing, vibrating around. And phase is all about the intermolecular potential energy of how, well bonded they are to each other, more or less. So make sure you're relating those things. Temperature goes with kinetic energy. Phase goes with potential. You can concept get through a lot of thermal physics just with that idea, as well as this little graph. Study the phase change graph. It's a great one. You can look at stuff like what's happening when temperature is changing versus what's happening when phase is changing, because remember, only one of those things will happen at a time. Picture what's happening with the molecules. Remember that like a phase change happens at constant temperature. That's your equation that goes with the phase change. That's your equation that goes with the change in temperature. So really studying that graph too is helpful. And thinking about what heat is. Heat, Q, is a type of work because it's how much energy like goes into a thing to heat it up maybe, or comes out of a thing as it's cooling down, or like condensing. All right, and remember how heat works. Heat flows from hot to cold if the 2 things are touching that are at the same temperature. In thermal equilibrium, no heat will flow. The greenhouse effect is another topic that comes up a lot and is a really good one to know. If you know the greenhouse effect, you can usually pick up a good handful of points when they ask you the greenhouse effect question. This one especially has a lot of keywords that you want to make sure you say. And remember, the word not to say is reflect. The greenhouse effect has nothing to do with reflection. It's this: greenhouse gases absorb and re-radiate the infrared light that comes off of the Earth because of its own temperature. And resonance is the property of the gases that lets them do that. They resonate, they like to vibrate at the same frequency as like infrared light does. Another thing to make sure you know is intensity is power per unit area. Not clearly really in the data booklet. That's sort of a definition one you want to know. So like watts per square meter is intensity. When we're talking about light, that would be brightness. So a lot of times they give you intensity stuff, like especially with planets and greenhouse stuff, because they have the solar constant in the front of the data booklet, which is a type of intensity, but it's like an intensity at the spot where the Earth is on some imaginary disk or some craziness. So anyway, a lot of times, remember, the trick to do is you take an equation like this, which has luminosity, which we've studied our data booklet. So we're like, oh, well, that's like a power thing. That's watts. If I need to do something with intensity, say like with the solar constant, and maybe I remember if I'm looking at a planet, I do the trick where I divide the solar constant by 4 to find the average intensity on the surface of the planet, like over the whole curved shape of the planet. To make this power over area, here's the trick. You can do L over A, because L is power, A is area. So intensity would be equal to this stuff, and you can like figure out temperature things. So the common one is they'll have you, estimate the temperature of a planet or something, just from the solar constant divided by 4, finding the temperature, and that's like the temperature without the atmosphere. And then maybe they'll have you talk about the greenhouse effect. Is usually how those go. But no, intensity is power over area, which means you can do this. Okay, other big stuff in the Unit C stuff, simple harmonic motion. Probably the most important thing to know about SHM is the definition. This graph is the definition of simple harmonic motion. If your acceleration is proportional to your displacement from equilibrium, you got yourself some simple harmonic motion happening. And it's got to be towards equilibrium is one way to say it, or A and X are always in opposite directions, meaning if you're displaced to the right, your acceleration's to the left. If you're displaced to the left, your acceleration's to the right. That's what is going to make you go back and forth and back and forth. And make sure you're also okay that simple harmonic motion is not the same thing as a wave. Like a mass on a spring is just a thing going up and down. There's no wave to speak of. It looks like a sine wave when you graph it, but that's just math. Okay, so the best way to think of this is like all of your equations in C.1 are they're about simple harmonic motion, which is like a single thing going up and down or back and forth, an oscillator. And oftentimes you'll use this for one particle on a wave. So if you got to find like the displacement of one particle on the wave, or its velocity, or its energy, or something, that's what all this C.1 SHM stuff is for. All the other unit C stuff is for the wave itself. If you want like the speed of the wave, the wavelength of the wave, so on, so on. So as you practice, try to make that distinction because it's easy to, you know, kind of mix them up or let them fuzz together in your brain, but try to kind of break it down that way. Okay, a couple of fields things. Field strength is force per something. Field strength is always a force per whatever. So electric field strength, remember, is the force per unit charge on a small test charge, yada, yada. G field strength is a force per unit mass. So these are other ones we're thinking about. The units can be super helpful. Newtons per coulomb, newtons per kilogram. We have our equations that tell us about this. Like here we see G field strength is force per unit mass. And remember, that means we can do our classic equation. Fg equals m times g just comes from this, the definition of what field strength is. And of course, remember, like if you're saying gravity as a number, that doesn't mean anything. That's not nearly good enough. You're going to screw stuff up. You got force due to gravity or weight on the left here. You got the mass of the thing here. And you got acceleration due to gravity or gravitational field strength here. Those are all completely different things. So hopefully at this point in your physics career, you don't have any issues about like mass versus weight versus acceleration due to gravity. And you're not calling any of these things just gravity because that doesn't mean anything. Yeah, so make sure you're okay with all that. Okay, and yeah, our equation for E field, this is force per unit charge. So we've done this a lot. Multiply the charge of a charge by the strength of the E field it's in. Figure out how hard it's being pushed by that field. That's when you know about the field itself. Remember, if we know about like the two masses or the two charges, we could also use Coulomb's law or lug to find the force between them. Okay, and another really good fields thing to look at is the crossed fields problem. This is a great one because it really shows you if you know the difference between like electric stuff and magnetic stuff because they're not the same at all. They're very related, but like a north pole has nothing to do with plus minus. Yeah. The electric force and the magnetic force are completely different things with completely different rules. So remember, like, you only use your right hand if you're doing magnetic force stuff. The electric stuff is maybe easier. Remember, the E field just shows you like which way the force would be on a positive charge. The B field, the magnetic field, is the one where you got to use your whole right hand to do. But anyway, review this problem, try this problem. It'll probably come up in the IB exams, and it's a great one to just make sure you're okay with how magnetic force works versus how electric force works and how their directions work and all that. Okay, and towards the back of the data booklet and such, atomic and nuclear, you need to know this. You need to know what an electron volt is. This is not really in the data booklet. If you don't know what you're doing, because it doesn't tell you 1 eV equals this many joules, but you need to do that conversion all the time. Maybe the best way to think of it is 1 eV is 1 E times 1 V. It's 1 elementary charge times 1 volt. That's the definition. It's like the work done on an elementary charge moving through a potential difference of 1 volt. So you multiply this number, the elementary charge, by 1 volt and get this. Yeah, but so again, like this number is in your data booklet, but in coulombs as the elementary charge, you got to know you multiply that by a volt. You get the size of an electron volt, which is an energy thing. That happens a lot. If you don't know that you can do that, you're leaving multiple points on the table probably, so make sure you're okay with that. Also, in terms of EV stuff, remember we have our other weird unit that's like a E equals mc squared kind of unit to use with that equation. That makes math life easy when we do that equation, but it's a little confusing because an MeV per c squared is totally different than an MeV. MeV is a unit of energy because that's just, a million EVs. But an MeV per c squared is a unit of mass because E equals mc squared. So m is E over c squared. You also need to know how the alpha particle, beta particle stuff, know what they are, know what the numbers are and why, and remember like which one goes for the beta particles. The electron goes with the antineutrino, and the positron goes with the regular neutrino. Good way to remember that is you always have like a regular particle and an antiparticle paired together, because the electron's like a regular, particle, and the positron is an anti-electron. So memorize all that stuff. Okay, and some HL stuff now. Okay, so when you're looking at these equations, just again, make sure you're okay with the equations themselves, and you can try your best when this stuff comes up on the exams. But V is velocity between your reference frames. That gets confusing sometimes when there's other stuff moving, and like the difference between V and U especially is easy to mix up. So remember how these work. It's like, somebody's on a train throwing a ball, and somebody's standing on the platform watching the train. And so like U and U prime would be the speed of the ball, the velocity, we should say, of the ball measured on the platform versus on the train. But V is the velocity of the train itself relative to the platform. All right, so V is always between the two reference frames. All the other stuff are like measurements of velocity or position or time as well, in terms of like the prime reference frame versus the not prime reference frame. Okay, and also in terms of just variable stuff, make sure you're okay with like delta t0 is the proper time. And proper time means you're measuring a time between two events that happen at the same place. So if you're not in a reference frame where like the thing you're timing, when you start the stopwatch and when you stop the stopwatch, if the thing you're timing didn't happen at the same place, it's not a proper time. It's got to happen at the same location. You got to be basically at rest with the thing to measure a proper time. Otherwise, you're measuring a dilated time. So you don't always have a proper time if it's not a thing where the two events happen at the same location. So you can only use that equation if you have a proper time. Same thing with proper length. You can only measure proper length if you're in the rest frame of the object. So if you're moving relative to the object, you cannot measure a proper length, and you would measure a contracted length, a shorter length. Okay, so at least know that stuff about relativity. Again, what the variables mean and like how to know if you have a proper time or a proper length. And that can get you a little bit of the way there. Some other HL stuff, the rotational piece, there's a lot of analogies you can draw. These are good to think about because if you understand mechanics, which by the way is like the most important topic to study and feel really good about anyway. But if you understand your mechanics stuff like Suvat equations, F equals ma, momentum stuff, you can very one-to-one relate that to all of the rotational stuff. Because remember, we got like rotational Suvat equations that look just like the SUVAT stuff, except with omegas instead of the V's and an alpha instead of the A. There's an F equals ma for rotation. It's torque equals I times alpha. So if you can tie these things together, it will really help when you study one in terms of understanding the other, and that kind of goes both ways. Yeah, so there's a couple, differences. In rotation, you're dealing with all the clockwise, counterclockwise stuff, but for the most part, thinking of how these things correlate to each other will help you a lot because the math, the concepts are very, very, very similar. Okay, some HL field stuff. There's a ton of equations and fields that are super confusing. All of these, you want to know at a minimum the name and the unit of like the different things you're looking at here. This is confusing because you got GM1 M2 over R squared, GM1 M2 over R, GM over R squared, GM over R. They're all completely different things, and you need to know what's what. Again, this is like bare minimum data booklet stuff, but like when they say gravitational potential, make sure you know that you're looking at this and not at this. Yeah, the units help a lot with this, and you can kind of see a pattern here too, because we got like a newtons and a newtons per kilogram. We got a joules and a joules per kilogram. So for these, here's my vector things, the first two. I got one where I have two things, and I got a solid concrete number about the force between the two things. Field strength is a more hypothetical vector, if you want to think of it that way. It's kind of a here's what would happen if you put a mass here. If the field strength is 10 newtons per kilogram, that's telling me every kilogram of mass you put here feels a force of 10 newtons. Same thing if I got an electric potential or a gravitational potential. This kind of number might be telling me every kilogram of mass you put at this spot will have this many joules of potential energy. And then here's the actual potential energy stored between two masses. So again, know the units and names of those things, which will at least get you started if you see a problem about electric potential. And speaking of potential, make sure you know that if you see this graph, you should get happy, because this is a graph where it's like there's only one thing to do on it, typically, which is to find the slope of a tangent line on the graph, because the gradient of this graph is field strength, is what these equations tell me. Remember, that's a very common thing to do with the graph if you're not just reading numbers off of it, is get yourself a tangent line. The slope of that graph is the negative field strength. All right, and last, some other random HL stuff. Thermodynamics, one good thing to know, again, a graph that if you see it, get excited because you're like, ooh, pressure volume graph with like a heat engine. I know the story. I got to take the area between, like inside the loop here. That's the work done in one cycle of a heat engine. Oh, yeah, that's a good piece of trivia to remember. EM induction, D.4, is one of these topics where don't spend a lot of time studying it unless you're shooting for like a 6 or a 7 or something, because your time is much better spent studying much easier stuff. But one thing to know, if they ask you about Faraday's law, say flux, say rate of change of flux. If they ask you about Lenz's law, say oppose the change. Those are the key words to make sure you mention if you're saying anything about those laws in any kind of question. And again, that's like if you're taking a wild shot and just trying to pick up a couple marks, those are the key words to make sure you're talking about when you're trying those questions. And for quantum, know everything there is to know about the photoelectric effect. Know this graph is a good one too. If you got your kinetic energy of the electrons versus frequency of the light graph, that you can like take the slope as Planck's constant and the intercept is the negative work function. And you want to know this in like very good detail as much as you can, because they get really into the weeds of all of what were the predictions of the wave model that didn't work out in the photoelectric effect, and why does the particle model explain it, and all that stuff. It almost all comes down to this one-on-one interaction. So if you really think about that and apply it, you can do a lot of photoelectric effect stuff. All right, so the whole concept is like an electron can only absorb a single photon. It's a one-on-one interaction, and the electron is either going to absorb all of the energy in that packet, in that blob of light, or it's not going to absorb it at all, and that kind of explains everything that's going on in the effect. Okay, so there you go. There are some of the really big, crucial things that you need to know going into the IB exams, on top of studying your whole data booklet. And once you get feeling good about those things, that's when you want to move on to the next level of finding some old practice problems. Pick a couple topics to specialize in, get good at those, but make sure you feel really good about this foundation, which will help you out a lot for the exams. They will be tough, but you will be ready. All right, so good luck, have fun.